Hi guys, I'm Mochi Zari from Seven Sky Consulting, and today we're going to talk about the exciting subject of stock prediction using machine learning. In this video, I'm going to talk about the LSTM model, how it works, and we'll make a simple implementation of it to see the results for ourselves. Before we dive into how LSTMs predict stock prices, let's first understand how it processes information. LSTMs are designed to remember patterns over time. They have two types of memory: short-term memory, also called the hidden state, and long-term memory, known as the cell state. The diagram in the background represents the flow of data through an LSTM cell, which consists of multiple gates: the input gate, forget gate, cell gate, and output gate. The process starts at the input gate. Here, the model takes in new stock price data and determines what information should be added to the memory. It filters the incoming market data, keeping only the most relevant features that could impact the future prices. Next up, the forget gate decides which past information should be kept and what should be discarded. For example, if a sudden market anomaly happened in the past but is no longer relevant, it will be filtered out here. In the cell gate, the LSTM combines new information with filtered past data. This updated memory helps the model understand trends such as whether a stock is consistently rising or fluctuating in patterns. Finally, we reach the output gate. This is where the LSTM decides what information to pass forward as the short-term memory for the next time step. This ensures that relevant trends are carried over while keeping computations efficient. To keep this video as short as I can, I've already written the script and we'll go over every detail of the code to see the steps we need to take in order to implement the model. Prepared a CSV file containing Microsoft stock prices, and we're loading it here in a pandas data frame. A data frame is a table-like data structure in pandas, much similar to an Excel sheet or SQL table. Since LSTM works best with normalized data, we're using min-max scaler from the scaler library to scale the closing prices between 0 and 1 for better computing. LSTM works best with normalized data. We're using min-max scaler from the scaler library to scale the closing prices between 0 and 1 for better computing. Now, the date column in our data frame is in string format, and we need to convert it into actual date time objects. This function here splits the data in year, month, and day and reformats it correctly. And we apply this function to our dataset and make the date column as our index. Next, we're creating sequences. LSTM requires sequential data, so we create windows of past stock prices to predict future values. A sequence is a windowed dataset. Instead of feeding one stock price at a time, we take 10 consecutive days as input and predict the next day. Next up, to evaluate our model, we're splitting our data into three parts. Training set, which is 80% of our data set, and it's used to train the model. A validation set, which helps fine-tune model parameters, and a test set used to evaluate final performance. That the data manipulation is over and our data is ready, we move on to building our model by importing the necessary layers for our LSTM models, such as LSTM, dense, dropout. We also import Atom for optimization and callbacks for early stopping and saving the best model during training. Now we build our model using TensorFlow class. We first put our first LSTM layer with 128 units that capture patterns followed by a dropout layer that reduces overfitting by randomly ignoring 20% of neurons during training. Another LSTM layer for deeper pattern recognition with 64 units. A dense layer, which is a fully connected layer to process extracted features here, and a dense layer that outputs a single predicted stock price. Then we compile our model using Adams optimizer with a learning rate of 0.001, mean squared error as our loss function, which measures how far predictions are from actual values, and mean absolute error, which helps track the average error size. After that, we set early stopping to stop training if validation loss doesn't improve for 10 epochs, and also a model checkpoint to save the best performing model during training. Now that we have built our model and prepared our data, we finally move on to training the model by passing it the training data and our validation data. Now, what this validation data actually does is that during training, the model evaluates itself on this dataset to check how well it's generalizing. It also helps monitor overfitting, which is when the model memorizes training data but fails on new data. After that, we set epochs to 100, which means that the model goes through all training data 100 times. And we set batch size to 32 here. This instead of updating weights after each individual sample, the model processes 32 samples at a time before making updates. This speeds up training while maintaining accuracy. And after that, we pass our callbacks, the early stopping and model checkpoint here, and we set verbose to 1 to display the training progress in the console. Once training is finished, we make predictions on the test data and visualize the results here. And finally, we measure how well our model performed by checking the root mean square error, which lower values mean better predictions. Now, let's run our model to see the results. Passed. Here it's building the model and also training it. We have a warning here, but it's proceeding. Now it's visualizing the results. Now, what can we tell from this graph here? As you can see, the predicted values are much smoother than the actual stock prices. This could mean that the model captures general trends but fails with short-term volatility, and also the model predictions fail to capture sharp fluctuations, for example here and here. This could mean that the model is not complex enough or lacks sufficient historical data to learn the stock movements. And also the use of min-max scaler might be at fault here because extreme values are compressed and it makes it harder for the model to predict large swings. Now, in my next video, I'm going to improve this model to get more accurate results. And thanks for watching this video. Make sure to like and subscribe and stay tuned for the next video.